Okay, let's look at some of the characteristics of this sine wave. Okay, I'm going to do my best to try and not have this get too cluttered, but a sine wave, an untransformed sine wave. So when you think about y equals sine of x, we'll start at the origin, go to its maximum point at 1, come back to touch the midline, go to its minimum point at -1, and come back to touch the midline. So the midline of this graph is at y equals 0, which is the x-axis, okay? And then you get up and down and back, right? This is 0, this is 2 pi. So there's our basic sine wave. What's happening here, right? Let's start on the outside. So we have this floating constant in the back. This is our vertical shift, okay? And a vertical shift takes the entire wave and just moves it up. So one thing, how do we identify that when we actually look at the graph? So the vertical shift is down, or I'm sorry, did I say up? Down, right? It's -1. So we would say it goes down 1 unit, right? And that moves the midline. So that's the biggest physical difference when you see a vertical shift, okay? That it's going to move the midline. So this line is literally moving down 1, which is going to take this entire graph and move it down 1. It's going to take all these points, move them down 1 unit, okay? So there's the vertical shift transformation. Let's stay on the outside and go over here to look at the amplitude, right? The coefficient here. This is our amplitude. So here we would say, and this is A equals 1/2. Sorry, I should have written over here, D equals -1. And an amplitude of 1/2, the amplitude is the distance from the midline to the max and the min, okay? So in a regular sine wave, the amplitude is 1. That's why the distance from this midline to this point is 1 unit. When we take the amplitude and we cut it in half, we only go up a little bit from the midline, okay? So I'm going to try to be as surgical as possible. These anchoring points, these intercept points don't move, okay? So we're essentially vertically compressing the graph, right? So we're flattening it out when we decrease the amplitude. So it's coming up, coming back to its intercept to here and to there. So you can see that the black curve is a little bit more compressed. Sorry, I should get both my arms here. A little bit more compressed vertically, okay? After we identify that, we want to know what the length of the period is. And the length of the period is based on the coefficient of B. Now, right now, if you're looking at this and you're saying there's no coefficient, understand that x over 2 is the same thing as 1/2 times x, right? We just slide the x into the numerator, multiply it times 1. So this means that B is 1/2, right? And to find the length of the period, which is one of the most important traits of a sine or cosine wave, is to understand the length of the period. The length of the period is found by taking 2 pi and dividing it by B. So in this case, that would be 2 pi divided by 1/2. And when we divide by 1/2, we multiply by 2 over 1. We take that half that's on the bottom, we flip it over, and we multiply by that 2. So here we would get a period of 4 pi. Let's talk about what that means in terms of the transformation. Remember how we talked about inside and outside transformations? We've talked about it many times this semester, okay? An inside transformation is a horizontal transformation. And when we're doing horizontal transformations inside parentheses, we do the opposite. I'm going to talk over Dr. Manola, okay? So when we talked about horizontal transformations, we said that we're doing the opposite, right? So normally when you multiply something by 1/2, you make it smaller, right? Well, if it's opposite state, we're actually stretching it. So we're not decreasing, we're not compressing the period by 1/2. We're actually multiplying the period by 2. So what happens is this graph, this black graph, is being pulled from the sides. So you can see if I can get this all on camera. Pulled from the sides and stretched out like taffy or a slinky, okay? And is going to go way like that. The wave is going to take a whole lot longer. So, and it's going to be hard for me to demonstrate this on this graph, but you're basically going to get a much more spread out wave. We'll see that here in Desmos in a second. Okay. The last thing that you're going to be asked for is the phase shift. The phase shift is the values that are both of the values that are inside these parentheses combined together. Okay. Now, C is the constant that we add or subtract here. And in fact, it's the constant that we're subtracting. So C is pi over 2, right? The phase shift, I'm going to have to slide down here a little bit. The phase shift is C over B. So in this case, it would be pi over 2 over 1/2, which is pi over 2 times 2 over 1, right? We take that half, we flip it over and multiply. Here we're going to get pi. Now what this means, okay, what is the definition of this phase shift? That's telling us that the graph, the first point, so you may want to write this down, the first critical point moves pi units to the right, okay? Because we had a positive phase shift, we're taking that graph and we're moving it pi units to the right, okay? So come back to here. What did we do? We shifted the graph down, we compressed the graph vertically, we stretched the graph out, and then last but not least, we have to take this and move it, okay? Pi units to the right. So all of those points are moving as well. In Desmos, right, what did we have? D was a value of -1. So there's the vertical shift. Come on. Very touchy. A is 1/2. Watch us compress this graph when A approaches 1/2. So there's the compression, okay? B was a value of 1/2 as well. So watch the graph stretch out this way. So there's the slinky motion when this is 1/2, okay? And then C was what? Pi over 2, okay? Yeah, pi over 2. Pi over 2 is like 1.5. So there's the movement of the graph over, to about right there. I can't move in terms of pi with what we have here. So here's the graph. Now, again, for the sake of comparison, here's sine of x, okay? So that's what the purple graph is what sine of x is supposed to look like. The red graph is what we're graphing, right? Smushed this way, moved down, shifted over, and pulled like taffy, right? Those are the transformations that we want to start to identify in these graphs so we can start to understand the waves a little bit more.